Hi friends, welcome back on our YouTube channel. Today in statistical mechanics we are going to discuss about energy fluctuation in canonical ensemble. In last lecture we have discussed about canonical ensemble. Now energy fluctuation in canonical ensemble. So here we will discuss about energy fluctuation in canonical ensemble. The average energy is given by U is equal to ensemble average of H equal to integration dp dq H e raised to power minus beta H divided by integration dp dq e raised to power minus beta H. Here beta equal to 1 upon kt and k is our Boltzmann's constant, whereas H is Hamiltonian. Now if we cross multiply this equation, then u integration dp dq e raised to power minus beta H is equal to integration dp dq H e raised to power minus beta H. Or if we transfer this from here to here, so integration dp dq u minus H e raised to power minus beta H is equal to 0. Since u is the function of volume and temperature, so it does not depend on p and q, so it can be taken into the integration and therefore we get this equation. Now we multiply on either side by exponential beta a. So the equation will be integration dp dq u minus H e raised to power beta a minus H equals to 0. So here we multiply with e raised to power beta a on either side. So e raised to power minus beta H into e raised to power beta a will be exponential beta a minus H, and H is the function of P and Q, whereas A is the function of V and T. Differentiating both sides with respect to beta, so we differentiate this equation with respect to beta. Therefore, first of all, integration dp dq u minus H is constant, and we differentiate e raised to beta a minus H with respect to beta. So differential of e raised to x is actually e raised to x, therefore e raised to beta a minus H. And now we differentiate this with respect to beta by using u into v method. So a minus H will be constant and differential of beta with respect to beta is 1, plus second time we differentiate this with respect to beta and this beta will be constant, so plus beta. H does not depend on beta because this is the function of P and Q. Therefore, its differential will be 0 and differential of A with respect to beta will be del A by del beta, plus second time this whole factor will be constant. So integration dp dq e raised to beta a minus H is constant, and we differentiate u minus H with respect to beta. Since u is the function of V and T and beta is actually 1 upon kt, so u is the function of beta. Therefore, the differential of u with respect to beta is del u by del beta is equal to 0. Therefore, differential of this with respect to beta will be this one. Since integration dp dq e raised to beta a minus H equal to 1 and beta del A by del beta is equal to 1 upon kt del A upon minus 1 upon kt square del t, because beta equal to 1 upon kt, so this beta is 1 upon kt, and if we differentiate this, then d beta is equal to 1 upon k is constant and differential of 1 upon t is minus 1 by t square dt. So this del beta will be minus 1 upon kt square del t, which is written here. So beta del A by del beta is this one. Now K and K will be cancelled out and 1t and t will be cancelled out. So beta del A by del beta is equal to minus t del A by del t. Now we replace this integration dp dq e raised to beta a minus h by 1. So this will be del u by del beta. Integration dp dq u minus h is written here and beta del a by del beta is minus t del a by del t. So this factor will be this one. Since integration dp dq e raised to beta a minus h u minus h a minus h minus t del a by del t is equal to ensemble average of u minus h whole square. So this is our ensemble average of u minus h whole square. Therefore ensemble average of u minus h whole square is equal to minus del u by del beta, because this is our this one. So if we substitute this value by this one, then we get ensemble average of u minus h whole square is equal to minus del u by del beta. Thus mean square fluctuation of energy is ensemble average of h square minus a square of ensemble average of h is equal to ensemble average of u minus h whole square is equal to minus del u by del beta. Since beta equal to 1 upon kt and d beta equal to minus 1 upon kt square dt, so this d beta is replaced with this one. Therefore ensemble average of h square minus a square of ensemble average of h is equal to kt square del u by del t, because this negative and this negative will be cancelled out and we replace here del beta with this one. So we get this value. Since del u by del t is equal to Cv, that is specific heat at constant volume or thermal capacity, so if we replace this del u by del t by Kv, then ensemble average of h square minus square of ensemble average of h equal to kt square Cv. For a macroscopic system, ensemble average of h is directly proportional to n and Cv is directly proportional to n. Therefore, this equation represents a normal fluctuation. So this equation represents a normal fluctuation. As n tends to infinity, therefore almost all systems in the ensemble have the energy ensemble average of h or u, that is internal energy. Therefore canonical ensemble is equivalent to the microcanonical ensemble. Now we use another method here. Since 1 upon h raised to 3n factorial n integration dp dq e raised to minus beta h is equal to integration 0 to infinity dE omega e raised to power minus beta e, and this is equal to integration 0 to infinity dE exponential log omega e raised to beta e, because exponential log omega is actually omega, so this omega e can be written as exponential log omega e. Now we combine these two factors, so we get exponential minus beta e plus log omega e. Therefore 1 upon h raised to 3n factorial n integration dp dq exponential minus beta h is equal to integration 0 to infinity dE exponential minus beta e plus log omega e, and this is equal to integration 0 to infinity dE exponential beta log omega upon beta minus e. So we take beta common here, and therefore this factor will be this one. Also, log omega upon beta equal to kt log omega, because beta equal to 1 upon kt. So if we replace this beta by 1 upon kt, so log omega upon beta will be kt log omega e. And log omega is equal to s upon k, because s equal to k log omega. So if s equal to k log omega and here s is entropy, then s upon k will be log omega e. So this log omega e will be replaced with s upon k. Now k and k will be cancelled out, so log omega upon beta will be ts. So this is our ts, and therefore 1 upon h raised to 3n factorial n integration dp dq exponential minus beta h is equal to integration 0 to infinity de exponential beta ts minus e. Here S is entropy defined in the microcanonical ensemble. So this S is actually the entropy which is defined in the microcanonical ensemble. Since entropy is directly proportional to N and internal energy is also directly proportional to N, and as N tends to infinity, therefore the maximum number of integrand occurs at E equal to E bar. So since S is directly proportional to N and U is directly proportional to N, and as N is very large or N tends to infinity, so the maximum of the integrand occurs at E equal to E bar. Now 1 upon h raised to 3n factorial n integration dp dq exponential minus beta h is equal to integration 0 to infinity de exponential beta ts minus e. Since ts minus e is maximum, and for maximum first differential will be 0, and first differential gives the condition at what point this value will be maximum. So del by del E ts minus e equal to 0. Now we differentiate this with respect to E. So t is constant and differential of s with respect to E is del s by del E, and differential of E with respect to E is 1. So minus 1 equal to 0. And from here t del s by del E at E equal to E bar equal to 1. For maximum, second differential is less than 0, that is negative. First differential gives the condition at which the value will be maximum, and second differential decide this value will be maximum or minimum. If second differential is negative, then the value will be maximum, and if second differential is positive, then the value will be minimum. So for maximum, second differential will be negative. Therefore del to s upon del E2 at E equal to E bar will be less than 0. So its second differential is this one, and this will be less than 0. Above equation implies that E bar equal to U. Now from here del s by del E at E equal to E bar equal to 1 upon T. So del to s by del E2 at E equal to E bar is equal to del by del E of del s by del E at E equal to E bar, and del s by del E is actually 1 upon T. So we replace this with 1 upon T. So del to s by del E2 at E equal to E bar is equal to del by del E of 1 upon T at E equal to E bar. And this will be equal to del to s by del E2 at E equal to E bar is equal to minus 1 by T square del T by del E at E equal to E bar. So the differential of 1 upon T with respect to E is minus 1 upon t square del t by del E. And it is clear from here that the value of second differential is negative. Since del u by del t is equal to Cv and u equal to E bar, so we replace this u by E bar and therefore del E bar by del t equal to Cv. Since here E equal to E bar, so del t by del E is equal to 1 upon Cv. So this is replaced by 1 upon Cv and therefore del 2s by del E2 at E equal to E bar is equal to minus 1 upon t square Cv. Thus, for satisfying del 2s upon del E2 at E equal to E bar is less than 0, Cv should be positive. Because if Cv is negative, then this negative and this negative will be positive, and in this case del 2s upon del E2 will be greater than 0. So for satisfying del 2s upon del E2 at E equal to E bar is less than 0, Cv should be 0, and it is true for physical system. Since Ts minus E is equal to Ts at E bar minus E bar plus 1 upon 2 E minus E bar whole square T del 2s upon del E2 at E equal to E bar plus and so on. So we expand this value and we get this equation. Since del 2s by del E2 at E equal to E bar is equal to minus 1 upon t square Cv and E bar equal to u. So Ts minus E equal to Ts at u minus u, because this is u and this is also u. So this will be Ts at u minus u plus 1 upon 2 E minus u whole square. So this is replaced with u into t, and del 2s upon del E2 at E equal to E bar is minus 1 upon t square Cv. So this is replaced with minus 1 upon t square Cv. So we get this value. Neglecting higher order term. Now we neglect its higher order term. So Ts minus E equal to Ts minus u minus 1 upon 2t Cv E minus u whole square, because this t and this t will be cancelled out. So this value will be this one, and we neglect its higher order term, so there is no higher order term. Since 1 upon h raised to 3n factorial n integration dp dq e raised to minus beta h is this one, and this will be equal to integration 0 to infinity dE exponential beta Ts minus E is this one. So this is replaced with this one. So in bracket beta Ts minus u minus 1 upon 2t Cv E minus u whole square, or this will be equal to 1 upon h raised to 3n factorial n dp dq e raised to minus beta h is equal to e raised to beta Ts minus u, which is this one, integration 0 to infinity dE exponential minus E minus u whole square upon 2 kt square Cv, because here we are differentiating with respect to E. So exponential Ts minus u is our constant, and we get this equation. And this equation shows that in canonical ensemble, the distribution of energy is a Gaussian distribution centered about the value E equal to u with a width delta E is equal to a square root of twice kt square Cv. So this equation shows that in a canonical ensemble, the distribution of energy is a Gaussian distribution. Since u is directly proportional to n and Cv is also directly proportional to n, therefore delta E upon u tends to 0 as n tends to infinity. Since u is directly proportional to n and n is very large, so u will be very large. Therefore, delta E upon u will be very small, or it tends to 0. As n tends to infinitive, the Gaussian function approaches to a delta function. Let E minus u equal to x. So, d equal to dx. Therefore, integration 0 to infinitive dE exponential minus E minus u whole square upon 2kt square Cv is equal to integration minus u to infinitive dx exponential minus x square upon 2kt square Cv. Because E minus u is x, so this will be exponential minus x square 2kt square Cv. And if we put E equal to 0, then the limit of x is minus u, which is here, and if E equal to infinitive, then the limit of x will be infinitive. Since n tends to infinitive, so u tends to infinitive, and therefore this limit will be minus infinitive. So integration 0 to infinitive dE exponential minus E minus u whole square twice kt square Cv is equal to integration minus infinitive to plus infinitive dx exponential minus x square upon 2kt square Cv. And since integration minus infinitive to plus infinitive dx exponential minus ax square equal to root pi by a, and here a is actually 1 upon 2kt square Cv. So a is this one. Therefore, integration 0 to infinitive dE exponential minus E minus u whole square upon 2kt square Cv equal to root pi 2kt square Cv. So this a is replaced with this one, and we get this value. Now, we replace this value by root pi into 2kt square Cv, and therefore 1 upon h raised to 3n factorial n integration dp dq exponential minus beta h equal to exponential beta ts minus u into root of 2 pi kt square Cv. Now 1 upon h raised to 3n factorial n integration dp dq exponential minus beta h is equal to exponential beta ts minus u, and this root of 2 pi kt square Cv is written as exponential beta 1 upon beta log of 2 pi kt square Cv power half, because if we open this one, then exponential beta into 1 upon beta log of 2 pi kt square Cv power half. So beta and beta will be cancelled out, and exponential and log will be cancelled out. So again we get this value, which is written here. Or 1 upon h raised to 3n factorial n integration dp dq exponential minus beta h is equal to exponential beta ts minus u plus half kt. Because this power will be transferred into multiplication, because here we have log and beta is 1 upon kt. So 1 upon 2 beta will be 1 by 2 kt, and log 2 pi kt square Cv is written here. On comparing similar quantity on either side, so if we compare similar quantity of this equation, then here exponential minus beta h, and here exponential beta and this whole quantity. So minus beta h equal to beta ts minus u plus half kt log of this one, and beta will be cancelled out. So minus h equal to ts minus u plus half kt log of 2 pi kt square Cv, or h equal to u minus ts minus half kt log of 2 pi kt square Cv. So we multiply this whole equation with negative sign, and we get this value. Since u equal to ensemble average of h equal to a plus ts, or h equal to a equal to u minus ts. So we transfer this ts from here to here. So h equal to a equal to u minus ts. So a equal to u minus ts minus half kt log of 2 pi kt square cv, because h equal to a equal to u minus ts. So this will be our a. So a equal to u minus ts minus half kt log of 2 pi kt square cv. When n tends to infinitive, half kt log of 2 pi kt square cv is negligible. In the limiting case, a equal to u minus ts, actually a is this one, but when n tends to infinitive, then this value will be negligible, and therefore a equal to u minus ts. Above equation shows that the entropy defined by canonical and microcanonical ensemble differ only by the term of the order of log n. Also, almost all systems in the canonical ensemble have the same energy, and that energy is equal to the internal energy of a system at a given temperature. In the canonical ensemble, we distribute the system in gamma space according to the density function rho is equal to exponential minus beta h. So in canonical ensemble, we distribute the system in the gamma space according to this density function. It is found that the density of point falls off as we move from the origin of gamma space. Here we end our session. In today's session, we have discussed about energy fluctuation in canonical ensemble. Goodbye.